Hello? Oh, okay, that's very. I guess that's my volume toggle. Okay. Thank you all for coming for this session. I'm going to present BITSInject, which is a tool that I formed. It lets a local administrator on the local system to run code as the local system user in session 0. It's a whole new way to abuse the bits service, the Windows bit service that we will talk about, to abuse it to run your arbitrary program as the local system user, and actually do many other manipulations on the jobs queue that Bits maintains. First, a couple of words about myself. I'm Dor Azouri, currently doing security research at SafeBreach in Israel. My experience in security involved many different angles. I started with data analysis to network research, and now doing mostly software research of good creatures and bad creatures. The bad ones, such as malware and ransomware, and the good ones, such as this Windows component. We'll start for those of you who are not familiar with this service. BITS stands for Background Intelligent Transfer Service. It is actually not only a service, it's a mechanism that is composed of the service, which is the client, and a protocol. The protocol is defined by Microsoft, it's called BITS, and it sits on top of the HTTP protocol. It adds some verb and headers to allow transfers over HTTP communication. So we'll start from the bottom. It is a service, a Windows service running in session 0 as the local system user, and it is here to allow other users to transfer files, to download or to upload. It is said to be intelligent. I didn't check for the real reason why, but I have some guesses. One is that it has many advanced features that you wouldn't expect from a simple downloader. It can handle retries for your transfer. It can handle proxy authentication. It can have your jobs can have expiry date of weeks and months, and many other recoveries that it does with itself. And maybe most notably, it is intelligent because it is meant to optimize the bandwidth usage. It gets many download and upload jobs to handle, and it calculates the right time to transfer each of the files. And it is run in the background. You just tell it what to do, which file to transfer, and it does it all alone. A couple of more bits about Bits. It is here with us since Windows XP, since 2001, and it evolved since then with 5 major versions. We're currently at version 5.0, which is not that recent. Version 5 came out at 2012. And it is used normally and very commonly for software to download their own updates. And the most notable use is Windows Update. Windows downloads its own updates using the Bit server, the Bit service. It has many advanced features. Some of them I already mentioned. And other users that are not Windows Update and that are very common are Google Chrome updates are using Bits, and Microsoft Office, and OneDrive, also of Microsoft, is using Bits for synchronization of files for both upload and download. You can see many of the main events that Bits produces in the event log when you filter the Bits client source. I'll start with a quick demonstration, not a demonstration of the tool. I'll just show you to get a glimpse of how Bits is operating. Maybe you never noticed it in your system. So for that, I'll open one of the softwares. Sorry about that. One of the softwares that use Bits. This is Hex Editor Neo. And sorry. When I open it, it looks for it checks for new versions, and it finds a new version, and you can choose to download. The download is done by Bits, and we will show you. The download has started, as you can see in the status line. We will go and see using the utility called BITSadmin. It lets you operate and see what's in the queue in the Bits queue. And as you can see, a new job has been created. Let us see. Wait. Okay, I didn't catch it on time. But what we would see here is a job created by Hex Editor that downloads a file from Hex Editor servers to a temp location, and then the editor handles and execute the update. And now for the demo of the tool itself, I will use the easiest flag that's in the tool. The tool is a Python script. It accepts many different parameters, and there's an easy mode to just give it a path of a command to execute, and it will be executed in session 0 as the system user. So I'll just put it here for a second. We start with a command as run as an administrator command shell, and we will go to the tool itself. Sorry. Now, as I said before, it has many different parameters to give, where you can create your own job and control the properties. And this flag gives us a very easy way to just execute, let's say, commands. We will go through the details of what are the different steps that it operates to get to the execution, and just for in about a couple of seconds we will get a pop-up. Maybe it will be only it's only on my screen. The pop-up just tells us that we are moving to a new that a service on session 0 is trying to communicate with the active desktop. Unfortunately, because it moves to another session, you won't see it there. But we have a video of that on the second demo afterwards. So we'll move on. Now, yeah. So the place that he's talking about is the session that we got into with a command spawn as system. We will later see another video demonstration that will show you that on Windows 10. So let's talk about some background terms that are important to understand the method. Bits can be used by many clients. It comes shipped with a BITSadmin client. Windows has it built in since Windows XP. It is now deprecated and it is replaced by PowerShell commandlets that are especially for Bits. Other third-party software, such as the one we saw before, are using it to directly communicate with the COM interface that Bits exports. All of them are operating and creating jobs, Bits jobs. Each job has a job owner. The owner is the user that originally created the job. If you use BITSadmin as user called user, that user will be the owner of the job throughout its whole operation. It can be of 3 types. download, upload, or a very special kind upload reply. All of the operations are done through the COM interface. BITS operates as a COM server, an in-proc server, a local server that accepts requests from different clients. The methods are exported by a QMGR proxy and the actual implementation is done in QMGR DLL. All of that is supposed to operate seamlessly with different users, trying to create and operate different jobs. And BITS has the job of maintaining this whole in a queue and even survive after crashes, after different events that are not in the control of the user. And for that reason, Microsoft thought that it is a good solution to use a state file on the disk. The state file is actually a presentation, a binary serialized representation of the job objects that are currently in the queue, and it is updated all the time on every job change. When BITS needs to rerun, for example, when you open the computer, it loads all the content of the file, it deserializes all the jobs, and loads it into memory and continue their operation. Serialization and deserialization has always been and is still a very fertile ground for injecting arbitrary data and expecting, well, unexpected behavior. And this is where this method sits, just trying to inject my own data to the state file and expect BITS to load it and operate just as I specially crafted the data. BITS had already known malicious users as a malware downloader. That's a straight use that you could imagine. I've seen a downloader that just invokes a command that uses BITS admin or PowerShell commandlets to download payloads, for example, and it is used as a persistency mechanism. A malware called Zlog is using a very key feature that we will talk about it, and it's very important to understand that feature because we use it as well. It's called the notification command line. BITS lets you define a command line that will be run when the job finishes, either finishes or turns into an error state. And this malware just added a job that defined a download of the same malware again and the execution of it. So even after you see and delete the malware image from the disk, maybe weeks and months after, you may see the same malware again running on your computer because the job persisted on the BITS queue. And it is a very good candidate for C2 communication. It uses just HTTP communication, and it is done by an OS service, so it's not always monitored. And it is very common to let the network controllers allow this kind of bits transfer because, as I said, it is used for downloading updates for Windows. So what was my inspiration to go and take that component into the research table? Windows Update. Windows Update uses bits to download updates, and Windows Update itself is a service running with the system privileges. And when you look at the queue while Windows Update downloads an update, you will see that the owner of the jobs of the Windows Update jobs is system. So I was jealous of how Windows Update does it because I wanted to do it as well and provide my own command line that will then be executed as system. So why in the first place do I want to get to that objective? Local system has some privileges that are above administrator privileges. To name a few, it can open a very important registry key and Hive, the security and SAM, where the NTLM hashes of the passwords are stored. If it is run on a domain controller, it has unrestricted access to all the object and object types on the Active Directory. and it has the network privileges of the machine, meaning it can identify itself on the network as the machine, as the OS itself. And it has covert identity because all of the actions are done as system. Not all of them are audited, and it is very hard to differentiate when you do forensics wise. It's hard to differentiate the good operations of the system and the malicious ones. More specifically, if we look and do who am I / all and see all the privileges that each of the users have, this is the difference. System has more privileges than the administrator. Also, to name a few, assigned primary token gives the ability to change the primary token of a process. Only the kernel and system can do that. Lock memory privilege lets you define pages in memory that will remain in memory and won't be paged into the hard disk. TCB privilege lets the process to act as the OS itself. There are others, we won't get into them. So what's the abuse that we are doing? I remind you, we want to use the feature that lets you define a command line to run. And that's called set notify command line. That's the name of the function in the COM interface that one should use to define a command line. And you just define a string that will be executed using create process as user, the Win API call. And the user that it will be run as is the owner of the job. So I will walk through the research process that I have made. And the first step that I tried was to just open a command shell as system in my own session. And the first thing that comes to mind is using BITSinject, the sysinternals tool. So I do just that. I created a job. And to give it a real meaning, I need to define the transfer that I want to make. So in this case, I want to download software exit to SYSTEM. Creating a job had no problem, and the command succeeded, but the second command failed with this exception. Unable to add file to job because the operation being requested was not performed because the user has not logged on to the network. At that point, I didn't know what that means, but I encountered a very absurd situation because when trying to cancel the same job using the same user, I got the same exception. So God, in this case system, created a rock, in this case a job that he cannot cancel. And that was my first hint to go into the state file itself, because that was my only way to delete that job. I deleted the file and it recovered just like when doing reset. We'll look more into the state file later, of course. Okay, so Wawang is the name of the Windows Update service. At this point, I wanted to try and figure out how Wawang succeeds in creating and operating a system job, and I can't using BITSinject. So my methodology here was comparing the two flows step by step and trying to find where it differentiates. So the normal flow would go like that. Wawang switches to the call context of the COM interface of QMGR DLL. This is how you use a COM inproc server in Windows. And then you can use the pointer that you get for the interface to invoke on that server different functions. So naturally, the first function that I want Wawang is doing is creating a job. And you can see in this screenshot, the dynamical to that function create job with the parameter, the static string WU client download. And this is exactly the description that you will see on jobs in the queue while Windows is downloading updates. The next call will be to add file, same as we did with BITSadmin. You want to give the real job to be done. And after you did that, the job is still not running, you need to call resume. This is where the job really starts to get into the queue and to be handled by bits. The last two calls are actually not called explicitly by the user. They are called in various occasions when Bits calculates and decides that it is a good time to transfer another chunk. I remind you, it handles many downloads and transfer jobs and wants to optimize the usage. So these are called repeatedly by the Bit service itself. So as I said, I compared the two flows, and the first call to create job was identical in parameters and identical in the result, in the outcome. Both succeeded, and a job was virtually created in the queue. The call to add file, as you probably remember, failed when used by BITSinject. The same parameters were given, but one failed. So this is where I wanted to dig in and find the difference between the two cases. So in short, and these two lines are the lines that I'm going to explain in the next slide. In short, the reason for that exception is a bad pairing of the client security identifier and the session ID. And don't get confused between SAD, the session security identifier, and the session ID. These are two different things. And the solution that I have made to overcome this situation that caused the exception is to fake the session ID. When the session ID is faked, we got to a good pairing of these two artifacts and got on with the execution. So what are the checks and enforcements that Bits requires for a job to operate? And it is these kind of checks are done on every crucial request, every crucial operation on the job, on creation, on adding a file, on resume, and many other calls. So access check, for those of you who are not familiar, is a very root and main function in the Windows security model. It is a Boolean function that returns either grant or deny, true or false. And it is used here as a COM server security enforcement using the interface called iServer security. This interface is given to any COM server that is used in the system, and it has a generic implementation of a co-impersonate client and co-revert to self that on impersonation takes and clones the token of the client thread, checks the client thread trustee, may it be a user, a group, or a logon session ID, checks it against the DACL list of the object that's in place, and returns either grant or deny. This is how access check works. An object has a security descriptor. Inside it, there's a DACL list with access list entries. So two threads are trying to get read, write, and execute permissions on the object. The first one is denied because, as you can see, the first entry says that Andrew is denied of read, write, and execute. You can't be more explicit than that. But the thread B gets the permissions because Jane is in group A, and as you can see, the second entry says that group A is allowed to write, and everyone is allowed to read and execute. If you combine them both, the requested access is given. So the first checkpoint was actually really a security enforcement. The second one is an enforcement that Bits defines for itself. It's not a generic, it's something that Bits decided to have. And it requires the requesting user to be logged on in an active session for the job to continue its operation. And for that reason, there's a check for the active logon sessions that are currently on the machine. So in this case, user called 1, as you can see in the arrow in the left, is in session 1. This is the regular session when the first user logs into Windows. And there's always another session, session 0, where all the system services and other application services are run. So how are we going to do that? In more detail, after the two checks after the first check has passed, we do the second check as follows. We want to switch to the logon token of the requesting client, of the client thread, clone it, and perform the action that he requested with the remote token. In order to clone it, Bits wants to find the pairing of the security identifier that's in the job object, that is the job owner, and the session ID from which the request was made. And to get the session ID, Bits uses the API call get token information. And when I used BITSinject, I didn't know that before, but apparently BITSinject is run with the system user, but in the active session that I invoked it from. In that case, this is session 1. And because system is not logged on in session 1, we got the exception. System is always logged on in session 0 and is never logged on in any other session. So my goal here was to try and mimic and replace the return that we get from get token information to session 0 and actually pass the test. So how do we do that? I debug the process service, SVC host. There are many. You find the one that runs bits, you debug it, and I put a breakpoint just before the call to clone user token, just before the exception is thrown. I do the same steps to create and define a job, and then we get to the breakpoint. And now, just as simple as that, I change the return value of get token information, that is 1, is stored in a place in memory. I just change it to 0, and the check, I pass the check, and at that point, the job is written into the state file. So I pass the check once, and the result, the actual valid job, is in the state file. I don't have to pass it again. And the fault here is that Bits, when loaded again, will load that job and won't do the check again. It just takes the content that's in the file, deserialize it, and performs what's in it. So that's how it's done. Session ID now is 0, and we pass the test. Just for future reference, a lot of the token manipulations and impersonations is done under a class called C-nested impersonation, and that eventually calls an win API call called impersonate logged on user with the token that was copied from the client thread. So after all checks are done, the action is performed using impersonation, and the server then gets back to self. But the job is now valid. It is in the queue. It is also projected to the state file. But the initial state of each job is suspended. And to move it from suspended to actual transferring of the job, you have to explicitly call resume. And there are many other states. There are some nuances between the different states. And there's an error and transient error. Error is a complete and final error, and transient error is a kind of error where bits can recover from. So our next obstacle that we need to overcome is to change the state of the job. If we and I tell you after checking that the state that we want to move into is either queued or connecting. When the job is on one of these states, the bit service will continue with the transfer. So, do you remember the first hint that I had to go into the state file? So I went into it. I reverse engineered the structure of the file. It's a unclear, opaque file that I had to try and make many attempts to understand where the changes are applied. And the file is located in this folder in a program data downloader. There are actually two files that are updated alternately. It's interesting, but I don't know the exact model of the decision when to update which. There's a kind of backup model here where when one is used, the other is used as a cold backup, and it's updated sometimes this one and sometimes the other. For all effective use that I needed, the one that's in effect on a current time position, a current point in time, is the one that's stated in this registry value. And what's the content of the state file? It is just a straightforward, unencrypted, and partially protected binary representation of the jobs in the queue. Why I say straightforward? Because this is how you're going to see a string representation. For example, the string of the job description. It starts with an integer that setting the string length in characters, the characters that follows, and the null termination character at the end. These kind of properties are written to the file with various codes to serialize and write. It is unencrypted, so when you open that file with an X editor, this is really what you're going to see. Nothing else to do here. And it is partially protected. What I mean here is that the file is used by a service that's running in the system scope. So as long as the service is running, a handle is present. A handle to the file is present from the service. So an administrator can really modify the file. But the same administrator has the right to stop the service. And when the service is stopped, the file can be modified. And then you get the service back on again, and your modifications are applied to memory when bits deserializes the file. What could be done better here is maybe put a kernel lock on the file, or at least have it with a trusted installer permissions. So now that we know how the file is structured, we found the exact byte that gives that represents the job state. We change it from 3 to 0, and now the job is queued. In general, these are the steps that we made. We stopped bits service. We replaced the file with the new modified file, the state file, and started bits again. This is what we see when we look at the output of bits admin list, where we see the whole queue of bits and just the important stuff. This is our job. It's called TTT. The connection, the state is connecting. It is owned by the system, and it is elevated with system integrity level. The command line that will be executed when the job finishes is what we saw before, just cmd exe. The integrity level, just as you saw here, is system. It is the highest integrity level. Just for those of you who are not familiar, the integrity level is another way for Windows to differentiate different users. Actually, differentiate the same user that acts with different integrity levels, and that's what, for example, gives the ability to have the UAC interface. An administrator can change the UAC operation, and that's something that's done with the highest integrity level. Okay, now notice that the method that I described meant that we are replacing the whole state file, meaning that any jobs that were previously in the queue are overridden, are deleted. So I wanted to find a way for injecting my own job, not interfering with other jobs. And in addition, I didn't want to have to debug the service on the machine that I want to do that on. If there's a remote computer, it's very hard to debug a service on the remote computer. But apparently, if I do it on one machine and take the state file to another machine, just copy and paste the same file to the same location, the same queue is applied in the target computer. There's some variations on different versions, but there's a finite number of versions. You can do a factory on your home system, home machine, and produce state files that represents queues that you want to be executed on another computer. Copy it to that computer, and this is what you'll get. That's a peek of how the file is, how the file looks, the structure of the file, the different parts of it, and properties of jobs that are currently in the file. This is a template that you can use. It's in the GitHub repository that's of this project, and you can use it to parse your own state files, both for Windows 7, 8, and 10. It is covered almost for all the properties that are there. So as I said before, I now want to push my own job without interfering with the other jobs. So also we know the file structure, and we found that in the queue header, there's a counter that says how many jobs are in the queue. We just increase it by one and find the place where a job ends and just before another one starts, and push our own job, our serialized job that we prepared, and we just added a new job. So BITSInject is the tool that will let you do just that. It will inject a new job to the queue. It will remove it when the job is finished. And one of the options that you can do is prepare a job that has the local system owner and the command line being whichever program that you want. It allows editing some other parameters and properties of the jobs, and some will be added in the future. And the next thing I want to talk about is the interactive session detection that we saw before. Actually, you didn't see, but you will see in the video. That's a mitigation that's in Windows since Vista, and it's actually a service, Windows service running in the background, and it monitors other services and pops up a message when another service tries to communicate with the active logon session. Because services don't have to communicate, shouldn't communicate with the desktop and the user session. So how do we overcome this? There are two possible ways. One is just to use a command, a program that we want to execute that is not interactive. It doesn't require opening a window. That way, the mitigation won't be triggered. Another way is just changing the registry value that says whether to have this mitigation or not. You can see the picture of the pop-up that we couldn't see before because of the move to the session 0. And now we'll see it with a prepared video. This time we'll see it on Windows 10. It works just the same. So we have a program called write file, which just writes a file called stub file to ctemp. This is the one we want to execute. We firstly look at the queue, and we see that there are no jobs in the queue, as you can see here. Now we use the script BITSInject to prepare a job called demo that will download this file to this location and execute this program. As you can see, I'm using a local server, and this should be a bit server. I didn't find any implementation of bit server in Python, so I wrote one. It's called simple bit server. It is also in the repository, and it can serve as a bits server. Now, the first step is to prepare the job. We give some of the parameters on the command line, and some are default, and a new job is created and serialized. This is the data that we want to inject into the queue. Then we run we inject it and run the bits service again. Now we stop, we pause on this part, and look at the queue. What we see here is our job demo owned by system connecting because we already made it change the status. This is the command line that will be executed as system, and this is the file to be downloaded. We continue with the operation. We intentionally made the server not have this file, so we get error 404, the file that you requested, the requested URL does not exist. It moves the job into error state, and this state means that Bits will execute the command line. As you can see, Bits actually tried 4 times. It is defined by default to do 4 retries. You can change that. And the next step would be to remove the job from queue. Actually, in this video as well, because of how the operating system is working, we can see that session. I'll try just to flip the laptop to the other side so you can see. But in this case, the program that we use wrote a new file, bits tab file, and as you can see, the owner is system. So I will have another try to use our tool and show you how it looks, because it's a very rare place to be, that session. I didn't see it before I tried that. So just a second. So again, I'm using the script, the tool, to have a command shell to be spawned with system in session 0. Let's wait a couple of seconds for the job to go into error state, just like we've seen in the video. And it won't work because I lost connection. Sorry. We'll try it again. I'll reset the queue just to make it clearer. And I'm connected again. Just a couple of seconds, it will go into error state. Here it is. Now I'll try to flip the laptop. We get the pop-up from the UI 0 detect mitigation. We click to view the method, and this session has nothing but, even not Explorer is running, nothing but the command, the program that we specified. In this case, this is the command shell, and if we press who am I, sorry about that. We press who am I, and we see that we are empty authority system. Actually, it is on now. Yeah. So as you can see, thank you. We are system. So anything we do under this process will be as system as well. Let us exit and return to the active session. And again, meanwhile, does anybody have a question? We have some more slides coming after. Okay, that's it. Great. Okay. Yeah, please. You mean when Windows Update uses bits? Yeah, so the URL is given with a secured, it can operate in both secured and non-secured way. And the downloaded file is, of course, signed by Microsoft, and the signature is checked. It was a good, it could be nice if you could just replace the job with a different URL and have your own file served, but Windows Update won't really run this file. Yes. No, so that's the thing here. I don't use any of the documented. Did I get you? Yeah, I don't use the interfaces because I just go into the state file and change what I want. This is a new kind of interface to control bits. So you'll see in the repository the simple bit server that, as I said, sits on top, inherits from a simple HTTP request handler, and it is used here, as I told you, to accelerate the time that it takes. Yes, I will get that at the end. Sorry. Okay, have it. Yeah, it is on GitHub. You'll see the link on the last slide. It was already, this talk in a shorter version was already given at DEF CON a couple of months ago. This is an extended version. I didn't get to go into details on the last one, and I got the opportunity to do it here. So the simple bit server is used to intentionally move the job into error state. And actually on Windows 10, you can do the same without creating any network traffic at all. And there's a check on the volume serial number of the destination path that you created. And if that check fails, it goes into error state. And you can just put a random string on that virtual serial number, and you get the error that the destination volume has changed. And actually, BITSInject checks if you run on Windows 10, and always prefers this method to not produce network traffic. So to sum it up, what were the conditions that made this method work? Or maybe the kind of things that could be done better. One is that the service relies on the state file data without verification. After the data is in the file, this is the controlling data. This is what will be executed. And a lack of unique machine identification. This is what allowed us to move the file from machine to machine without changing anything, without needing to provide any other parameter. Another problem is the integrity of the file, the state file, that, as I said, is done and operated by the system, but can be modified by an administrator that can stop the service. And the last one just made the whole thing easier. The file is just a clear, straightforward serialization of the objects. Along the way, I found another cool thing you can, cool way you can abuse bits. At this time, you can make it fail when it tries to download. And the good use for it is to choke the folder where Windows Update needs to download the update to, and make it fail. The way for doing that is that because bits, before it downloads the content of the file, it creates a hidden file, a temporary file, and with a name convention as follows: bit, and then 1 to 4 characters, hex characters. And if you calculate, there are only about 70,000 different names that you can that are valid in this format. So if you, it's kind of a race. If you know where a file should be downloaded to, you go and create 70,000 hidden files with all the options, and Bits just fails with not that indicative reason. If you see it on Windows Update, it says that some updates were not installed, and the error found Windows Update encountered an unknown error. So you get deprived of specific Windows Update, and when we look at it from an APT group perspective, this is a good way to weaken the security of the machine, because if you didn't get the update on, I think it was on last May, you are vulnerable to WannaCry. And you can use, similar to how BITSInject works, you can use it to change job properties, change job states of jobs that are already in the queue, and completely remove a job from the queue. The response I got from Microsoft when reporting that to them is that a malicious administrator can do much worse things. And if you really look at the definition that they have on vulnerabilities, they say that an administrator, if you're already an administrator, you can do whatever you want. I get that. But as I showed you before, there are some privileges that system has that administrator doesn't. They could do maybe a bit better to mitigate that. This is where you can find the tool, the code, the white paper, and the simple bit server. You can find me in email and in Twitter. And thank you very much.